relation. Let's call this as, I denote it by tilde. What is it that it will do? It will take two elements from S, okay, and it will say whether it's related or not, right? So essentially, let me not make it very formal. And an equivalence relation, this, okay, right? Is that fine? So in the earlier case, I wrote it as a double arrow, okay. So what are the properties of this equivalence relation? You take any two sets, right? So you can either say A is related to B or not, right? So okay, let me put that in the context of itself, right? What are the properties? So A is related to A for every A in S, right? A is related to B implies B is related to A for every AB in S. And the third one would be A is related to B and B is related to C implies A is related to C for every A, B, C in S, right? These are the properties. Do you agree? Fine. So now we
Yes,
have
sir.
to prove that this divides into the entire class into equivalence classes, right? So how do you write that? How do you collect these things? Okay, the way you do it, you can do it mechanically, right? So fix some A in S. Okay, I'll take some arbitrary A. Okay, so I'll consider an equivalent class, let me call it as EA, okay, which is defined as all those B in S, that is the states in S, such that A is related to B, right? So in other words, if A can talk to B and B can talk to A, then I'll put that B into this set. Obviously, A can talk to A, so therefore A clearly belongs to EA, right? This is very clear. Fine? Is that okay? Ayush?
Yes, sir.
Clear, right?
Yes, sir. Yes, sir.
So you
Yes,
take,
sir.
so now the idea is this ES partitions, yes, okay. That is, what do you mean by that? If you take, for example, EA and EB, okay, so you take two sets. Either either EA will be equal to this, or if you take intersection of these two, it will be null. Okay, this is what you should prove, right? You agree? Now, can you try to prove whether this either of them should happen, right? If you take A and B, right? So, for example, suppose let's look at two cases now. Suppose A communicates with B, that is B belongs to EA, right? Then we need to prove that EA is same as EB, right? Do you agree? Then I won't even prove, you can see this clearly, EA equal to EB. Why is that the case? Can somebody tell me? What is EB? All those states which can be communicated from B, right? What is EA? All those states which can be communicated from A, right? Suppose B belongs to A, what does that mean? So B can communicate with A, but all those states which B can communicate, A can also communicate, right? Therefore, EA should be equal to EB. Do you agree? Is that
Sir,
fine? Yes.
uh, sir, if there is a state C and
Hmm.
that also communicates with A, but
Huh?
here we are partitioning it into EA, like EA is partitioning S. So then C will not be able to communicate with A then.
No, if, for example, C belongs to EA, right?
Okay.
Then C can communicate with A. It can go back and forth from A to C and C to A, right? That means C can also communicate with all those states that A can communicate. That is, all those states in EA, it can communicate. Therefore, by definition, so if you construct a set EC, EC will be equal to EA, right? So think of it as individuals as states, and if they hold hand together, then they are equivalence class. Okay. So the claim is equivalence class partitions the entire group into two parties, right? Not two parties, multiple disjoint parties. What is the worst case scenario? One party, right? Everybody holds hand with each other, right? I mean, in other words, if there are four people, A, B, C, D, then A can talk to B and B can talk to C, C can talk to D, and vice versa, right? That forms a chain. It is one group. If you want to have two groups, what do you mean by that? Essentially, there is a breakage of link, right? So let me give you an example, then it will be clear, I think. So I take states 0, 1, 2, 3, 4. Okay. So let's look at these things. Sorry. Okay. You can put appropriate probabilities. Okay. In all of this, such that the probabilities are non-zero. Okay. What can you say about this? 0 can talk to 1. 1 can talk to 2. By the property of equivalence, 0 can talk to 2. We proved this, right? Do you agree? Therefore, 0, 1, 2 belongs to the same class. Do you agree? That means E0, it is all those states that 0 can talk to. 0 can talk to 1 and 1 can talk to 0. Therefore, 0 and 1 are in the set 0, E0. So, E0 is same as E1 is same as E2. Do you agree? Okay. Let me call this as E1. Okay. What about E3?
Sir, here 0 cannot talk with like 2 directly. So E0, how it is
No.
E0 equal
So
to E2?
you remember the definition. So what do you mean by 0 talking to 2? That means P0 to 2 in some step n is greater than 0. For example, I'll just give everything as half, okay? Half everywhere. Okay. What is the probability that it can go from 0 to 1 to 2? This is at least 1 by 4, right? At least 1 by 4. Right? So which is greater than 0, right? In what? How many steps? 2 steps. So P02 in 2 steps is greater than 0. Therefore, 0 can communicate with 2. And similarly, 2 can communicate with 0. Why? I can start at 2 and go to 0 in 2 steps with a probability of at least 1 by 4, which is greater than 0. Therefore, 0 can talk to 2 and 2 can talk to 0. Therefore, they communicate with each other. Do you agree?
Yes, sir.
Okay. So it's not about communicating in one step. It's communicating in n step, any n. That's very clear. Ayush?
Yes, sir.
Huh?
Yes, sir. Yes, sir.
Okay, fine. So now let's look at E3. So 3, 1 can communicate with 3, right? For example, this could be 1, for example, okay? So not 1, maybe it can go out, or I don't know. Did I make a, okay, so 1 by 4, and let me make it as 1 by 4, okay? So 1 can, starting at 1, you can go either go to 2 or either go to 0 or can go to 3, right? But from 3 you cannot come back to 1. Do you agree? If you are in 3, you are gone.
Yes,
I
sir.
mean, there's no way by which this would be 1 1, right? You go back and forth, let's say. So that means E3 is nothing but 3 and 4, right? 3 can talk to 4 and 4 can talk to 3. Therefore, it's same as E4. Okay. But clearly, if you look at E1, so let me call this as E2. E1 intersection E2 is null. Do you agree? Because E1 is 0, 1, 2. E2 is 3 and 4. They are disjoint. It has broken this entire set into two parts. This is one set of states or communicating class. This is another. Right?
Yes, sir.
Is this fine? So you can, the argument is very clear, right? So EA equal to EB, or this is true. So for example, if A belongs to or B belongs to EA, then that means B can communicate with A, and therefore it can communicate with all the other nodes that A can communicate with. Therefore, B belongs to all the states in EB also belongs to EA, and vice versa. Therefore, EA equal to EB, right? On the other hand, if B does not belong to EA, right? The other part would be if EB does not belong to EA, that means what? It cannot communicate back and forth from any states in EA. That means if B can communicate with any other state, those states cannot communicate with the states in EA. Therefore, all those states don't belong to EA. Therefore, EA is not equal to EB and they are disjoint. Right? Even if you say that one element belongs to EA, then all the elements of EB belongs to EA. Therefore, EB equal to EA. Right? Is this clear? I mean, you have to write it a little more formally, but this is the argument. Argument is clear. That's very important. Ayush?
Yes, sir.
Okay.
Clear, sir. Clear.
Yeah. So this is what you mean by splitting or equivalence. So the communication, this symbol forms an equivalence class, and therefore it partitions. Okay. Okay. Now let's start with a few other definitions. There is one more definition. This results in something. So there is this notion of recurrence and transient. Okay, we will see what those things are. Okay. Okay. So what do you mean by a recurrent state? So for a given Markov chain, a state. Let's consider some state I is said to be recurrent. Recurrent, as the name indicates, it will occur again and again and again. That means it will come back to state I again and again and again. Okay, and is recurrent if so what do you mean by recurrent? If I can communicate with J, implies J can communicate with I. Okay, is that fine? That means if I can talk to J, then J should be able to talk to I. Then only we say that I is recurrent, and that should happen for every state, right? For example, 0, is it recurrent or not? See, 0 can
Yes,
talk
sir.
to 1 and 1 can talk to 0, therefore 0 is recurrent. What about 1? What can you say about state 1?
No, sir.
No, right? It can talk to 3, but 3 cannot talk to 1, therefore it's not recurrent. So 3 is also not recurrent, but 4 is recurrent. So 1 and 3 are transient states, while 0, 2, and 4 are recurrent state in this case. Okay. So I is said to be recurrent if I communicates with J implies this. This is true for all J in states as yes. Okay. Set of states, yes. So otherwise we say that I is transient. Because why is this transient? So for example, if you are at 1, there is a chance that you will never come back to 1, right? So you'll go to 3 and you are stuck there, right? But whereas if, for example, well, is 3 recurrent? Sorry, I think is 3 recurrent or transient? We made a mistake. Okay, that's the hint. So is 3
Transient
recurrent?
only.
It's transient, right? Because 3 cannot communicate with 1. It says if I communicates with J, then J should communicate to I. But 3 does not communicate to 1. Therefore, I don't need 1 to communicate with 3. No, right? So 3 is not, so I'll mark in red those that are transient. Okay, this one is transient because the moment you hit 1, there is a chance that you will never come back. All right, so that's a transient state, whereas 3 and 4 are recurrent. Okay, because the moment you hit 3, you will come back again and again, infinitely often, right? Okay, is that fine, everyone?
Hello, sir. So I can
Yes.
talk to J and J can talk to I. This is the notion of equivalence also, right? Not implied and. I mean, is there an and between them?
Correct. So that and means communicating. But what it says is, if I can talk to J, then J should be able to talk to I. Then only we say that I is recurrent. Okay.
Okay.
Yeah.
Okay.
Okay. Any questions? Okay. So you know what a class is, right? Hmm?
Sir,
Yes, sir.
Yes.
so this definition of recurrent, this just implies the communicate like we have defined above, no sir?
So it should belong to a communicating class, but there is another requirement, right? For example, see, I communicates with J. That always that should imply J should communicate with I. If you look at the previous example,
Mhm.
see one. What can you say about one? Well, is this a class? I mean, that comes to this question. So, is this thing that I have marked, right? This whole thing, is it a class? 0, 1, 2. So, what is a class? Okay, so equivalence relation or the communication double arrow will partition. So, what will it partition? See, 0, from
States.
0 you can go to 1, and 1 from 1 you can go to 0. So the 0 and 1 belong to the same set. 2 and
Yes
1
sir.
also belongs to the same set. So all these things belongs to the same set. But
Yes
3,
sir.
4 does not. I mean, it belongs to the same set. This is fine, right? So what is a communication? So this is called communicating classes. Okay. What is your question, Sumit?
No
I,
sir, actually I'm saying we have defined the communicate like
hmm,
both double arrow side, no sir? Like
correct.
I double arrow
Ah.
J. Then sir, this is and this here we are defining that I connects to J implies J connects to I. This both implies that they are just communicating with each
Correct.
other only.
Exactly. 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 See, for example,
So,
one communicates with J, 3, but 3 does not communicate with 1. So, therefore, 1 is not
yes, sir, one
recurrent,
is
right? 1 is not recurrent. Do you agree?
yes, sir,
Hmm?
yeah, because if it is recurrent, then it has to be 3 to 1 also.
Yeah, exactly.
Mm.
Hmm?
Hello, sir.
Yes.
Sir, can you again define the definition of a class?
Okay, I'm going to do that. Okay, so this is
Okay.
called a communicating class, right? 0, 1, 2 is one, and 3 and 4 is another. Okay, so let's see what is a communicating class or a class. A class, C, is a subset of S. See, S is the set of all states. Okay, I'm taking the. In fact, class C is a non-empty subset. If you want to be very precise, you cannot take an empty subset. Non-empty subset of states, such that now, if you take I belonging to C, if you take this thing and you take any J, okay, not equal to I, okay, any state J not equal to I, then such that if I'll write it as if you take a state in C in the communication class and you take any other state not equal to I, then either J should be able to communicate with I and therefore J belongs to C, or J does not belong to C. Okay, fine. J satisfies what? J communicates with I, okay, and therefore J belongs to a C, okay, fine.
So that means, sir, a class will be a set of states which can have
Communicate with
equivalence
each other.
relation within each with each other.
They can communicate with each other. That's all, right?
Uh,
Then J satisfies this. So if J not equal to or, okay, or J does not belong to C. That means J, I communicate with J implies J, that is, I and J does not communicate with each other. Okay. Is that fine? Do you agree? Think of in terms of pictures. Okay. So if you have, if you belong, if a state belongs to that particular class, then it can communicate with all the other nodes in the class, and it cannot communicate with the neighboring, right? So for example, you look at 4. See, 4 cannot communicate, can communicate with 3, but cannot communicate with 1 or 0 or 2 because there is no path there, right? I cannot go from 1 to 1, or 4 to 1, or 4 to 2, or 4 to 0, right? Forget about that. I cannot go from 3 to 1 also, right? Therefore, they belong to a separate class. Is that fine? Everyone? Rishabh?
Yes, sir. Yeah.
Okay. So now, what does this lead to? So let's we have two notions now. One is the notion of class, and the other one is the notion of recurrent. Okay, so what does that imply? So this results in a theorem. Okay, so or a result. So I'll state this and explain. Okay, for a finite Markov chains, either all states in a class